thanks for coming. So I'm very pleased to introduce Sergey Norin from McGill University. And this is the second time for him to visit Korea. And, happy to host him again. And he will talk about asymptotic dimensions. Please.
Thank you very much for the invitation. So I'm gonna talk about the joint work with Zdeněk Dvořák and with Chun-Hung Liu. So these are two separate but very related results. And the main theme of this is that we want to get something like a nerve theorem for the dimension of intersection graphs of geometric objects. And I mean, this is very vague, and maybe none of the words I've used so far make precise sense yet, but I'll try to make this picture clearer and hopefully to motivate why would one care about this. So first of all, I mean, what is dimension? Well, so we understand well dimension of vector spaces, but what is a dimension of topological space? What properties do we want the answer to have? A natural property that we expect is that Rn has dimension n. And another property that's useful is that it should be a topological invariant, right? That's what it would mean to be a dimension of topological space. So it's invariant under continuous deformations. And even though, I mean, this question sounds basic, I mean, I haven't thought about it ever, and when I thought about it for the first time, I was surprised to know that, to see that I don't actually know the answer. And there are several ways to define it, but one popular notion is a Lebesgue covering dimension. And it defines dimension of its topological space as minimum n such that every cover of the space has a refinement of order or of ply at most n plus 1. And let me explain what it means, I guess mostly in pictures. Every open color has an open refinement. So
I'm sorry, but what does the PLY mean?
Yeah, I'll explain.
Okay.
So I need to. It's so ply of a toilet paper is how good it is, right? How thick it is. So ply means how many layers. That's what it would mean. So we have a cover of our topological space by open sets, symbols, and the condition is that whatever color we choose, we can refine it, so replace it by another, I'm not going to draw too much, but still cover, smaller cover, means every set here belongs to one of the sets here, and apply at most n means that at most n plus 1 means every point belongs to at most n plus 1 sets in the refinement.
So maybe you didn't need to refine your first picture.
Yeah. So, I mean, it depends. Here, maybe I refined this. Here I had points in 3 sets, and here I drew little enough that
Yeah, we probably
was
need
2 sets, but
Yeah,
of
but
course, because it's
It's the plane, no?
it's a board, I need to have. Fair enough. Okay, so I mean that's a good notion of dimension of topological space, but we want a notion that works for graphs, and this covering dimension. An important thing about it is that it's a very small scale dimension. So it really only cares about what happens if you look very closely at your space. So in particular, right, you can only consider refining covers which are already very fine. And for graphs, I mean, if you think about it, this dimension is not going to be particularly meaningful. Because if you think about a graph as topological space, discrete topological space, it has this dimension 0. Even if you glue in the edges to think about it as a topological space with, you know, lines between vertices, it still has dimension 1, and it's not a very interesting notion. So what would we like what properties would we like for dimension of a graph or a graph class? So what would be a good notion of a dimension of a graph or a graph class? Because as it will turn out, the notion of dimension that actually works is only meaningful for infinite graphs. But I dislike infinite graphs. I mean, I like infinite graphs, or I like finite graphs. And the way to talk about uses infinite notions for finite graphs is to look at a whole class of graphs. And it will be clear in a bit. So what might we learn from this dimension? Something like this. Say if we take an n-dimensional grid, let's say infinite. So this is 2-dimensional. So a grid in Rn should have dimension n. Right? That's a natural notion, right? Unless we really think about graphs as one-dimensional objects, in which case dimension is not interesting, something like this makes sense. And so the way, let me digress for a moment. The way Zdeněk and I came to this topic is somehow from a different direction. We wanted to understand geometrically, in some way, classes of graphs with strongly sublinear separators, or so, in some sense, we wanted some notion that for which grids in n dimensions somehow and objects of bounded complexity, and say expanders, which don't have good separators, are objects of unbounded complexity. And then a few years ago, the notion from group theory got an eye of graph theorists, and it seems like a really good notion, which had a lot of properties which we wanted. And then the notion, the concept of asymptotic dimension, which was introduced by Gromov in 2003.
So I'm sorry,
Not
but-
2003, yeah. My notes say Gromov 1992.
So can I?
Yeah?
Yeah. So for the Lebesgue covering dimension, it seems to me like a triangulation, while if you are thinking about grid graph, it looks like a product somehow. So it is in one space you are looking at the simplexes, and another space you are looking at the boxes or the products.
Yeah, and
Yeah.
so the point of these topological definitions,
Yeah.
and
Yeah.
that would be the case,
Yeah.
is that those are independent on, and that's kind of one of the things that I actually care about. They're really independent largely of the way how you partition your space. As long as you partition it kind of nice and uniformly, you should get the same result. So yeah, it's not going to distinguish much between triangulations and other ways to partition. But so let me just say Gromov. The definition of asymptotic dimension is not the nicest definition. So if my talk wasn't exactly about this topic, I would try my best to avoid defining it altogether. But it is, so I will define it. But let me sell it to you first. Before I say what asymptotic dimension is, let me tell you it has nice properties. So here is the theorem, which really I think is the nicest theorem in this field of large-scale or coarse graph theory, which recently became popular. It says that graph classes of bounded tribits, so tree-like graphs, have asymptotic dimension, well, one, right? You expect trees to be one dimension. And graph, proper minor closed graph classes. So graph classes, meaning classes of graphs which forbid a minor. I mean, if you know the Robertson-Seymour structure theorem for proper minor closed graph classes, they graphs in these classes, they decompose in a tree-like fashion into graphs which are embeddable on surfaces, so two-dimensional like. So they look two-dimensional, and they have asymptotic dimension at most 2. So this is a theorem by many people. I'm going to say names but not write them. So it's by Bonamy, Lebesgue, Esperer, Groundland, Liu, Perot, and Scott, published in 2023. So it shows, and I mean it is a very non-trivial theorem, very nice theorem, which shows that this notion behaves exactly as you expect. And a couple more pieces of evidence that shows that this might be a good notion. Graph classes of polynomial growth, and I'll define it, of degree n. So what does it mean? It means if you look at a vertex and you go distance r from it, then you should encounter at most some constant independent on r times r to the n vertices within distance r of any given vertex. So the balls expand at most at polynomial rate of degree n. So these graph classes have asymptotic dimension on order of n, which you expect. So grids z to the n have this property. So again, this is right. This is a result, it's implicit, so it's not said in this language, but close, by Krauss, Gaiman, and Lee from 2007. And again, that's non-trivial. And finally, it says there is a result of Gromov. This is from 2003. Is that bounded degree, the class of bounded degree expanders, so say cubic expanders, has unbounded asymptotic dimension. So this is Gromov 2003. So if your graph is, say, a random cubic graph, then that has huge dimension. It doesn't look like anything low dimension. And again, that's something that you might expect. So it feels like the right notion. So maybe it's worth investing into defining what is this asymptotic dimension. Okay, so let me define it. So let X be a metric space. I will say that D, a function from non-negative reals to non-negative reals.
Also, Sergey, what happens, say, if we forbid this topological language subdivisions?
But then you can be a bounded degree expander, right? Right? I mean, if you forbid a subdivision of degree 4 graph, you could be a cubic expander. That's important. So I say that a function is an so this is going to be the main technical definition. Well, one of the more technical definitions. An n-dimensional control function for x if the following holds. If for every non-negative real r, which is the radius on which we focus, the following holds. So it's going to be, again, in terms of covers. But now we are kind of, instead of going in and refining, we are coarsening, in some sense, going out. So there exists a cover let me write it as script u, which decomposes into a disjoint union of n+1 subsets of x. So you can cover the whole space by a collection of sets, which it's good to think of it as it's colored in n+1 colors, such that every ball of radius r, so it's not only a cover, it covers the whole space well, of radius r belongs to some element of u. So that's one property. The other property, where the function actually comes in, every element of script u has a diameter at most d of r. So elements of my cover have bounded diameter in terms of r, and finally the elements of ui are pairwise disjoint. And let me maybe make a picture. So we have a cover of the whole space, and let's say n is 2, which is, I'm not going to do a very realistic picture. So we are covering everything with 3 families. I'm not going to quite succeed, I think, here. This is U2, and then, so within each family, the sets are disjoint, and individual sets are of bounded radius. Okay, so something like this. This is U3, and moreover, I need to not only cover all the points, but also, so every ball of radius r must be covered by something. So they cover everything with a margin. You can think of corresponding to r.
The first condition should be ui or something? For every ui, the ball should be...
U is a union, so every ball of radius r belongs to some element of u.
Then where did you use the partition? So in the condition where?
In here, so within ui, the elements are disjoint, but elements of u1 are free to intersect many other elements of u2. So yellow bits are disjoint from each other and have bounded radius. Green bits are disjoint from each other, but I don't care how yellow and green things are.
Do you have a requirement? So when you say cover, do you mean each element of UI is open set, or?
Here I don't care about open and close. This is about metric. So I mean, I can actually fudge things a bit. It's also so rough scale, so rough. The subtle things like open don't matter.
So UI is just collection of something.
Yeah, this is just something. Okay, so that's an n-dimensional control function, and so the asymptotic dimension, so this is asymptotic dimension. So as dim of x is a minimum n such that x has some n-dimensional control function. So, which means that for every r, I can choose d of r. Now, this notion, why is it called asymptotic? This is large scale. It only cares about large scales, doesn't care about small scales at all, because I can choose for all r at most 1 or at most 1,000 d of r to be something enormous, a million. And so it only cares that I can cover every ball of radius 1 by some enormous ball. So it really doesn't care how exactly your space behaves on small scales. In particular, I can replace my whole space by a discrete space by choosing, say, maximal subcollection of points at distance at most 1, at least maximum the one net, right? Maximum collection of points pairwise distance at least 1 from each other, and that will have the same asymptotic dimension. It will behave exactly the same. So or I can change 1 to a larger number. So it really only cares about how things behave at very large scales. In particular, these two notions are unrelated. You can cook up spaces where, I mean, they really just operate in completely different worlds. One is very micro, the other one is very macro, even though they're in some sense similar, right? They care about in how many layers you cover everything. And there is somehow an intermediate notion which can be defined in this sense, which is relevant for us a little bit. It's a Nagata dimension. So let me denote it by A and dim of x. This is minimum n. Minimum n such that x has a linear n-dimensional control function. Which means so that it just means that there exists C such that d of r equals C times r is an n-dimensional control function. And this works on all scales now. So certainly a Nagata dimension is an upper bound on asymptotic dimension, and it's also an upper bound on Lebesgue covering dimension, which is less trivial, but it's doable. So if a Nagata dimension is small, then both the large scale and small scale dimensions are small. So that's the two things I want to say. So first of all, it works on all scales, and secondly, a natural thing which is not too difficult. One direction, which we probably care about more, is not too difficult. Is that a certain Nagata dimension of Rn is the right thing. So the fact that it's at most n, you can just exhibit a nice cover on every scale. Well, it's scale invariant, so just enough to do it on one scale. The fact that it cannot be smaller, I think it's some reasonable topology. You need some version of Sperner's lemma. Okay, so that's what asymptotic dimension is. And now, so that explains the dimension in my initial sentence. Let me try to say a little bit, even though it's it's a stretch, it's a bit loosely related, but I like this concept of nerve theorems. They're nice, and I want to present our result as potential variant of them. So let me, and it kind of shows why one would care about intersection graphs. So what are nerve theorems or nerve type theorems? They are theorems in topology which say that if you take a topological space, you can replace it sometimes by a simplicial complex which preserves a lot of its properties. Let me now be more concrete. So it's something like an intersection graph, but in topology you need more. So let F be a family. I mean, in general, you need just to be sets or subsets of the topological space. Then the N of F, so the nerve of this family, is a simplicial complex. And simplicial complex, I mean, in the end we'll only care about graphs, but I'll show you one example of slightly higher dimension of the following form. So simplicial complex just means it's a collection of sets closed downwards. So it consists of all sets I, subsets of indices, such that, so we take those collections of subsets in F or indices for which the intersection is non-empty. So it's something like intersection graph, but we allow super hyper edges. So we take those I for which intersection of the corresponding SIs is not empty. So it's some collection of subsets closed downwards, and from this you can construct a simplicial complex. Which, let me first draw an example, and then I'll actually say some theorem. Let's look at a sphere. So not a ball, a sphere. And let me look at the following subsets of it. So let me take a top hemisphere. That will be S1. And a bottom hemisphere, I can make them open, but let me actually, for the clarity of the picture, leave a bit of gap between them. So kind of top hemisphere, but a little bit away from the equator, and bottom hemisphere. And then let me do more sets. So S3 will be west hemisphere, and then S4 east hemisphere. And finally, this still doesn't cover it as a whole. Let me also look at the front hemisphere and back hemisphere. or just put a somewhat smaller patches, S5 in the front, and there is some invisible S6 at the back. So what is the corresponding simplicial complex? The nerve of this family. So the opposite guys don't intersect. But any subset that doesn't include a pair of opposite has an empty intersection, right? So if we say direction, say north, east, and front, we find a point in this direction. Actually, we find a little disk which is on the intersection. So if I look at the corresponding simplicial complex, I see this 1, 2, 3, 4, 5, 6. I have edges corresponding to all the pairs except the opposite pairs. And I also have the faces. These are also simplices, right? They correspond to non-empty intersection. So I get a surface of an octahedron as a nerve. So this is F. This is the nerve of F. And here is a nerve type theorem. I guess it's due to Leray, and if I say it more precisely, I guess due to Borsuk, is that if F is a cover of some topological space X, here it's a sphere, such that any intersection of subfamily in F is contractible or empty. And I mean, if you don't know what contractible precisely is, just think nice. So if any intersection is like reasonable, doesn't do anything weird, then the nerve of F, considered as this simplicial complex, but not abstract, as I drew it with bits glued in, is homotopically equivalent. Means topologically the same, but not quite, to X. So you can replace your complicated space by this reasonable finite-ish thing, which is roughly the same. And I mean, theorems like this are really, really useful in topological combinatorics. So, motivated by this, and partially motivated, so we wanted this initially, Zdeněk Dvořák and I wanted this bounded asymptotic dimension. So we wanted this bounded asymptotic dimension to serve as certificate of somehow being a reasonable geometric object graph. But what about in the other direction? Having reasonable geometric structure, does it lead to bounded asymptotic dimension? So that's one question that we try to answer. But in the same direction, are there nerve type theorems for asymptotic dimension? If you take a space and somehow reasonably cover it by stuff, subsets, and construct the corresponding simplicial complex, will it have a similar asymptotic dimension? Now, here is good news. We only care about metric and only on large scales. So we don't actually care about any faces we're gluing. We only care about graphs. So we only care about intersection graphs. Right? We don't care about high-dimensional faces. So that's the question. So does asymptotic dimension of intersection graphs of reasonable subsets of a space resemble the dimension of the asymptotic dimension of the space? And here is a beautiful, in preparation, theorem of James Davis, which says very much yes when dimension is 2, at least when the spaces are 2. And that's a difficult theorem, so he's been writing it for a while. Asymptotic dimension. Oh yeah, I defined, let me backtrack a bit. I defined the asymptotic dimension of a metric space, but I already said I want to talk about graph classes. So what is an asymptotic dimension? In the also previous results, which I talked about graph classes, what is the asymptotic dimension of a graph class? You can think of it as asymptotic dimension of disjoint union of all the graphs in this class. So of this one big infinite graph. That's valid. Or perhaps more naturally, you just think about existence of a single n-dimensional control function which works for all the graphs in the class. So you don't have to work with union, you work with each individual graph, but asymptotic dimension is at most n of a class if there exists an n-dimensional control function which works for every graph in the class, where each graph is considered as a discrete metric space. Naturally, distance between adjacent vertices is the shortest path distance. Okay, so now back to the theorem. It says that asymptotic dimension of the class of string graphs and what are string graphs? String graphs are just intersection graphs of strings, of connected subsets of the plane. So these are intersection graphs of connected subsets of R2 is 2, is what you would want, is exactly the dimension of the underlying space. You cannot hope for better. It's easy to see that just the grid has asymptotic dimension 2, but that says that it holds for all string graphs. So this is really kind of a very nice nerve theorem, right? The intersection, the asymptotic dimension is same as of this space. Now, I mean, is it true in higher dimension? Is it just harder? I mean, it's unfortunately false. I mean, every graph is an intersection graph of connected subsets of R3. Because you can you put a bunch of points, and then the points that want to connect, they put tentacles toward each other and connect. So this doesn't work in R3 or higher, but it needs need geometric objects to be nicer. And just, connectivity or any simple connectivity, contractability, nothing like that would work. You really need them geometrically to be nice. But here's, the nicest possible set of objects, probably just balls. Right? So what is the asymptotic dimension of the class of intersection graphs of balls in Rn? And we can almost answer this. Okay, so now let me actually state the definition that precedes our first theorem with Zdeněk. So basically, if you think about it, what happens is that you cannot allow kind of the lone scene objects geometrically. You want your objects to be roundish. And here is the definition that worked for us. So let f be a function, let's say from non-negative reals to non-negative integers. I will say that a family f of subsets of a metric space is f space filling. So the big F is the family of subsets, the small f is a function. If for every R and S, every ball of radius R intersects at most f of R over S, pairwise disjoint elements of script f of diameter at least S. Okay, this is obvious, right? Let me pause a little bit and try to see what it means. So we have a ball of radius R, and it says that I cannot stuff too many disjoint things of diameter at least S in this ball. So they actually fill space. They are not thin and long. They cannot poke from some directions. There is only bounded number of them, bounded in terms of this ratio, R to S. So the family of balls of any radius, of balls in Rn is F space filling for some reasonable function. So, given a ball of radius R, you cannot put too many balls of radius S which are pairwise disjoint and intersected, right? There is some bound, just volume count, right? Because they are all in the ball of radius R plus S and then okay, and I'll state this theorem. So it's a theorem of Zdeněk and myself from, we did it 3 years ago, but it's published this year, so it's 2020. So let X be a metric space of a solid Nagata dimension n, and let f be so let first of all small f be some function, don't care what it is. And let script f be an f space filling family of subsets of X, then the asymptotic dimension of intersection graph, but let me still use n nerve for notation. So this is intersection graph. Is at most 2n plus 1. Okay. So intersection graph just means so my points correspond. So let me just draw a picture. So here is some family, say, of balls in R2, and then I construct a graph by putting a vertex for each object in my family and putting an edge if they intersect. So, okay, so let me tell you a couple of things about this theorem. It's not quite a nerve theorem, so it was a stretch. I mean, it doesn't say that my metric space, my properties of my space quite the same as in the intersection graph. I need my metric space to have bounded a solid Nagata dimension, not asymptotic dimension. But that's reasonable, because maybe my whole business, my whole family, just lives in a tiny, tiny ball on the micro scale. So I need to control the behavior of my space on the micro scale, so that's why. And the bound that comes out is a bound on asymptotic dimension of the intersection graph, which is, and we cannot do a solid Nagata dimension. I mean, for various reasons. I mean, in particular, just because the graphs don't behave, I mean, they don't have any meaningful behavior on a micro scale anyway. But there are other reasons. I mean, because our function is not linear and other artifacts are true. But it tells us that asymptotic dimension of ball intersection graph in Rn is at most 2n plus 1. So at least it's controlled by the dimension. And so on the same order. And also, I mean, it's at least, here is another kind of hopefully positive evidence. If you look at the subtrees of a tree, which are hopefully sufficiently space filling, I mean, they should be reasonably space filling, then a tree as a metric space presumably has asymptotic dimension 1, or solid Nagata dimension 1. Then this says that intersection graphs of subtrees of a tree have bounded asymptotic dimension, at most 3 here. It's a bit loose. But still, I mean, what is intersection graphs of kind of subsets of a tree? I mean, it kind of resembles, in some sense, bounded Trevis graph. So it's relative of the theorem that asymptotic dimension of bounded Trevis graph is bounded. In fact, it's somewhat. Okay, I don't have that much time, but let me just tell you something about the follow-up work and
just a
questions.
quick question. So do you think that it might be possible to replace 2n plus 1 by n?
Oh yeah,
In
so
the same-
that's
the
what
main.
I'm gonna say.
Okay. The other question is, if you took the whole nerve, would it be reasonable to think about Aswad Nagata dimension coming out, or is instead of taking the intersection graph, or that might be?
That's a good point. I mean, you need to have a cover, I guess.
Yeah.
I haven't thought about it.
Okay.
That's a
Yeah.
good
I
point.
just okay.
I'm kind of lying about chronology here, internal. We proved this before I knew anything about
Oh, I
nerves.
see.
I'm pretending like that.
Okay.
So, yeah. With Chun-Hung Liu, we improved this bound to n plus 1 instead of 2n plus 1. And this is tight. So, so this is closer to what we want for the truth, that asymptotic dimension of any family of balls, say in Rn, is at most n plus 1. And what do I mean by that? It means there are space filling families for which you cannot do better. But space filling families are actually artifact of our proof method. Like we need to work with space filling families, and maybe I very briefly mention it rather than mention another result for technical reasons. But for balls, the answer should be n, right? So, and that's kind of the big open question here. We just don't have methods. I mean, we invented these methods which work really nicely, and for them n plus 1 is tight. So here is a big open question. I mean, do intersection graphs of balls really, capture asymptotic dimension of the space perfectly? So is the asymptotic dimension of the class of intersection graphs of balls, or if you like cubes more, you can do cubes, but I think balls are like in Rn equal to n. It's at least n, it's easy to show. So now we know it's at most n plus 1, but you need to invent something more to improve it. I almost out of time, so let me really very, very loosely say maybe about proof method of this. So, I mean, where is graph theory in all of this? Here, I'll try to show you. So here is what happens. What happens when you want to understand this control function for a graph at a radius about a half or 2/3 between a half and 1. So you want every ball of radius a half be covered. So let's say by one of the elements. So for every vertex, let's assign it a color correspond to the family the ball around it is covered. Now every element of U will have bounded diameter, but because balls of radius a half around every vertex is covered, every monochromatic component must belong to the same set. So every monochromatic component must have bounded diameter. And kind of in saying this, I captured both of these sentences secretly. Because what I mean is that if I have two vertices joined by an edge, then the corresponding balls intersect, so they must belong to the same element of U. Right? Cannot belong to different because different would have intersected. So if I do it at a radius of half, all I need is to color my intersection graph in n+1 colors, so that components have bounded diameter.
I'm curious. So if you two vertices have the same color,
So I'm coloring the vertex a color, so every ball of radius a half is captured. So I color a vertex by the color of the set that contains this ball.
yeah.
So if two vertices have the same color, the sets of the same color contain balls of radius half around them. These balls intersect, which means the corresponding sets intersect, so they must be the same set. So that's just a problem about color in a graph with bounded diameter. And now I'm out of time, but let me really quickly fudge it. So now I have to color in 2n+2 colors my whole graph. But my space is of a solid Nagata dimension n. So I can, in some complicated way, color covers of it in n+1 colors. So I use this n+1 colors to create n+1 tree decompositions in some complicated way. Right? Because I need to do it not on one scale, but on all scales that capture all my sets. So I decompose my graph into n+1 graphs of bounded trivets. It's a lie, but something like that. And then I apply bounded trivets result. That's a very high level overview. But that only does it for me at radius a half or something. I need to do it at every radius. And that's going to be the last thing that I say, but that's what I want to say. That's what F-space filling is for. I need a definition that's invariant by changing the radius. If I replace my sets by unions of all the sets that are within distance r from them, I will get a family of the same sort, but with a different function. So really, the coloring problem solves everything because my definition of F-space filling is survives in some sense changing the radius. Okay, and that's very loose overview of what we do. Okay, that's it. Thank you.
Thank you. Any questions?
So I have two questions. I'm not sure that this question really makes sense or not, but so for example, like if you look at not the intersection graph, but look at the nerve, so some high-dimensional skeleton of the nerve complex, then do you think that the asymptotic dimension has a similar kind of value, like n+1 or n, or maybe?
Yeah, asymptotic dimension doesn't care, right? That's what the thing is, right? It inserts in the faces, doesn't actually change. It only inserts kind of this lower, like very local things. It doesn't change metric at large distances. So asymptotic dimension doesn't care, but a solid Nagata dimension might, and it might matter.
So for another one, for the open problem, do you think that so if I replace the balls with parallel axis parallel boxes, for example, that is also meaningful open problem?
Then it's false. Going to be
Okay,
false. There are
false.
some examples. You need things to be round-like. You shouldn't allow things to stretch very long in one direction. I think we have some examples even for axis parallel boxes. But I mean, I'm not. I need to think. But yeah, I do believe we have examples that might be. Not completely sure because I'm mixing in my mind two problems. So, yeah, somehow we studied this in another related context, and there it's definitely bad, but it might be bad for reasons which are unrelated to asymptotic dimension. So I'll need to think a bit more.
What about something like codimension 1 disk or a ball of
Okay, that's something that I want to talk about, very similar to this. So Angelos Georgopoulos asked last year, what about spheres? What about asymptotic dimension of sphere intersection graphs? And those are not space filling at all, right? You can stack a lot of spheres within a ball. But that second result we have with Chun-Hung Liu is that in very, very broad setting, asymptotic dimension of intersection graphs and intersection graphs of boundaries are the same. So we can replace objects by boundaries and doesn't change asymptotic dimension. And that kind of, so that says that spheres and balls are equivalent problems, and disks could, certainly they can be bound. I mean, they're not quite bound. I mean, it's a bit not the same, right? Spheres clearly bound, roundish thing, but disks don't, so I don't know.
Okay.
I mean, I guess, I don't know.
Other questions? You mentioned your motivation was something about sublinear separator.
Yeah, so for example, I mean, is it true that every class with strongly sublinear separators has bounded asymptotic dimension? I think we don't know. I mean, I'd like it to be true. I mean, that would be super. I mean, we want some nice geometric property of a class of classes with strongly sublinear separators. And that was our best hope because of how nicely the theorems turned out. It's open.
I see. So you don't have any other example where you don't know whether asymptotic dimension is bounded, but has a strong sublinear separator?
Yeah, we don't know. There is this. There is another big open question. Is this fat minus question? So one can. So minor closed families have asymptotic dimension at most 2. But being minor closed is not a parameter that is not a large scale parameter like asymptotic dimension. Right? So having a minor is very small scale. One can somewhat technically define a natural large scale notion of not having a minor. And then an open question is, excluding this coarse minor, does it give bounded asymptotic dimension? That's open. And that's a very important, I think it's a very nice open question, but hard.
Any more questions?
So
Yeah.
maybe can you replace ball by some others kind of semi-algebraic set or something like this? I guess.
I mean, it shouldn't stretch too much, right? I don't want, right? I mean, certainly long lines are
So
bad,
the
right?
boxes and the boxes are not true.
Yeah.
Boxes with some bounded ratio.
Yeah, I think bound ratio is roughly equivalent to balls.
Okay.
Basically, I mean, if you can stuff it between 2 balls of comparable radius, I think it's as good as a ball.
Yeah. And they will probably be space filling.
Yeah, but I mean, yeah, space filling is not good. Yeah, we need to something better than space filling for the argument to work.
All right, any more questions? If not, let's thank the speakers.